In this study, we conducted 3 different shaped steering experiments to examine the usefulness of throughput and effective parameters for steering tasks. When people use computers, they always have implicit subjective speed accuracy biases. For example, some people try to complete a task accurately, and some people try to complete it more quickly. Such biases pose a problem in experiments comparing the performance of input devices. For example, it becomes unclear whether the improvement in speed or accuracy is due to the device or to the bias. Establishing a method for comparing device performance that accounts for the effects of subjective bias will contribute to a fairer device comparisons for the HCA field. The speed and accuracy of the operation will vary with the bias, but the performance should be constant. In other words, the bias will change the balance between the speed and accuracy trade-offs, and the overall performance should be somewhat constant. To calculate the performance for pointing task, Fitz proposed the index of performance measure. This measure is calculated from the speed and accuracy parameters and can combine the 2 factors of speed and accuracy into one as a performance. The fact that this measure was fairly constant across different task conditions is consistent with the hypothesis that human performance is nearly constant. Fitz IP calculates performance based on the accuracy required by the task, but it is not certain that users will actually follow the accuracy required by the task. For example, if the users complete a task with less accuracy, the reduced accuracy increases the speed. However, IP calculates their performance using the nominal task accuracy, so it does not account for the reduced accuracy by the user's strategy, and the calculated performance is inappropriately high. For pointing research, effective parameters were used to express the actual user accuracy. Effectiveness expresses the actual user accuracy as a spread of the endpoint distributions. For example, lower user accuracy causes the endpoint distribution to be wider, and higher user accuracy causes the endpoint distributions to be more concentrated. Previous pointing research has suggested that effective width may allow for modeling the effects of intentional user speed accuracy biases. Effective amplitude expresses the user accuracy as the actual target distance. When users try to complete the task faster, they are expected to try to shorten the task distance, so effective amplitude calculates the distance reduction as a decrease in accuracy. However, the effect of effective amplitude is smaller than that of effective width. By calculating the performance using the effective parameters, throughput is calculated. This throughput describes the user's performance because it represents the actual accuracy that can be completed per unit of time. By this calculation, throughput can smooth the effect of the user's intentional speed accuracy biases. Then, throughput can be used as a performance metric because it allows for the fairer performance comparison by smoothing out the effect of the participant's implicit subjective speed accuracy bias. However, GUI tasks are not only pointing tasks. Trajectory-based tasks which completed the task by drawing a trajectory also exist. The steering task is a typical example of trajectory-based tasks. For example, navigating in a hierarchical menu, using the lasso tool, or drawing a line. Establishing the theoretical validity of effective parameters and throughput in a trajectory-based task has the potential to enable fairer performance comparisons through trajectory-based tasks. This could provide a stronger indication of input device superiority or determine the better device for each task. Last year, we defined the definition of the effective parameters for crossing tasks. This definition is theoretically based on the fact that the movement times of both pointing and crossing tasks are modeled by the same Fitz law. We transfer the definition of effective width and effective amplitude of the pointing tasks to the crossing task by adapting them to the definition of the W and A used in Fitz law. The movement time of steering task is modeled by the steering law. The steering law is based on the theoretical foundation of an infinite sequence of crossing tasks. In other words, the steering law is modeled as an infinite sequence of Fitz tasks. Thus, it should be possible to transplant the effective parameters of the Fitz tasks to the steering task in the same procedure as the modeling. Then, using the same procedure, we derive the effective parameters for the steering task from the effective parameters for the crossing task. By this derivation, the definition of effective width for steering is the width that encompasses 96% of the variance of the stroke trajectory perpendicular to the direction of the task movement. The definition of effective amplitude is the total distance of the stroke's trajectory. These definitions hold consistently even if the path contains curved lines. By transferring fit throughput to the steering task in the same way, the throughput for steering is derived. This calculation retains the definition of fit throughput as the actual accuracy that can be completed per unit of time. To verify the validity of our definition of effective parameters and throughput for steering, we conducted 3 experiments with 3 shapes of steering tasks: linear, circular, and sine wave. All experiments were conducted with a stylus, and in all experiments, we gave all participants 3 intentional speed accuracy biases. The definition of the task conditions was consistent for all task shapes. A is the length of the path center line, and W is the path width based on the path center line. Because the path width is based on the center line, the areas near the inner diameter are self-occluded in the circular and sine wave shapes. This is based on the definition of the steering law, and the shape is not intentionally changed. The parameters specific to sine wave shape, wavelength, and amplitude were set to 68.02 and 19.89 mm to prevent these 2 parameters from independently affecting the experimental results. Here are the detailed setups for the experiment 1. We recruited 12 university students and we gave 3 intentional speed accuracy biases to all participants. For accurate, they complete the task as accurate as possible without considering speed. For neutral, they complete the task as accurate and as fast as possible. And for fast, they complete the task as fast as possible without considering errors. The specific conditions of A and W are shown on the slide. We recorded coordinates of trajectories with a timestamp. Here are the setups for the experiment 2. All conditions except for the task shape was the same as in experiment 1. In experiment 3, one participant was changed due to unavoidable reasons unrelated to the experiment, and we adjusted aids so that the start and end positions are always at the peak of the wave. We compared the baseline steering law model, the IDN model, with the IDWE model, where only effective width was applied, and the IDE model, where effective amplitude was also applied. For linear, effective width improved the model fit for mixed, but worsened the model fit for each individual bias. Effective amplitude had little effect on the model fit. For circular, effective width improved the model fit for mixed, but worsened the model fit for each individual bias. Effective amplitude improved the model fit for each individual bias, but had little effect on mixed. For sine wave, effective width improved the model fit for mixed and fast, but worsened the model fit for accurate and neutral. Effective amplitude little bit improved the model fit for accurate and mixed, but slightly worsened the model fit for neutral and fast. Consistently for all task shapes, the effective width improved the model fit for mixed. To investigate the effect of effective width on model fit, we analyzed the IU measure. Consistently for all task shapes, the IU was increased the more speed was emphasized. This result shows that the more speed is emphasized, the less accurate the movement becomes and the more positional variability of the trajectory increases. It was expected that the more speed was emphasized, participants would use wider width, and this tendency was observed for all task shapes. In fact, the model fit for mixed was improved by WE for all task shapes. In addition, we analyzed the IU between index of difficulties. Just as the difference in movement time between the biases increased with increasing ID, the difference in IU also increased with increasing ID. In other words, effective width may well represent the changes in accuracy due to bias. This is because considering the speed accuracy trade-off, the effective width which changes in opposition manner to the change in speed is likely to be the accuracy parameter. However, compared to ID versus MT, the linear regression is poor, which may be the reason for the decreasing the model fit by applying effective width at each bias. We also analyze the IU measure, which is calculated from effective amplitude and A. For linear and circular, effective amplitude was increased the more speed was emphasized, and for sine wave, effective amplitude was decreased the more speed was emphasized. It was expected that the more speed was emphasized, the more participants tried to shorten the path, but this tendency was only observed for sine wave. In fact, the model fit for mixed is slightly improved by effective amplitude for sine wave, while it was worse for linear and circular. We also analyze the IU between ID. Especially for circular, the effect of shortening the path by stroking near the inner diameter of the circle under the wider W conditions is evident in effective amplitude. This may account for the improved model fit for each bias in circular. In summary, when speed is emphasized in the steering task, users tend to focus on moving the stylus faster at the expense of increasing the positional reliability, rather than strategically shortening the path. We also examine the stability of throughput across biases. This is because the stable throughput across biases allows fairer performance comparison by smoothing out the influence of participants' implicit subjective speed accuracy biases. For all task shapes, the effective ways improve the stability of throughput across biases, and the effective amplitude have little effect on the throughput. Thus, it is recommended to calculate throughput using the effective width. The highest stability was found for the sine wave task, suggesting that the device comparison experiment using the sine wave task may be able to compare performance more fairly. This is because bias effects are less likely to appear in the calculated performance for sine wave. We analyze the stylus speed and the positional reliability to investigate the reason for the differences between the task shapes. For linear, the stylus speed was very fast and unstable across trials, and the positional reliability of the stylus was very small. In other words, participants moved the stylus very fast like a ballistic movement, which should have decreased accuracy, but the positional reliability of the stylus was so small. Therefore, the accuracy calculated by WE and the performance calculated by throughput became too high. In circular, the stylus speed was not very fast and was almost stable across the trials, and the positional reliability of the stylus was widely spread. In other words, participants moved the stylus in a collective movement based on the visual feedback, rather than in a ballistic movement as seen in linear. Therefore, more stable throughput was calculated compared to linear. However, positional reliability was increased in some parts of the path in easy trial. This may be due to the occlusion problem where the stylus tip is occluded by the hand. In circular, this problem always occurs in some part of the path. This was one of the reasons we added the sine wave, which contains a curve but is free of this problem. For sine wave, the stylus speed was not very fast and was almost stable over the trials, and the positional variability of the stylus was widely spread. In other words, as with circular, no ballistic movement was observed and a stable throughput could have been obtained. In addition, there was no increase in positional variability during the trial as seen in circular. This may be the reason for the more stable throughput than circular. Our limitations and future works are as follows. The path shapes are not only linear, circular, and sine wave, so additional validation is needed with other shapes such as corners, narrowing and widening tunnels, and sequential linear path segments. Furthermore, additional research is needed to investigate the effects of curvature. We should also investigate the effect of the amplitude or the number of waves of the sine wave. Finally, our implications are as follows. When modeling steering tasks with untested path shapes, we recommend using the baseline steering law model for estimating the movement time. However, considering the effect of the participant's implicit bias, it is recommended to use one device, one group of participants, and one specific speed accuracy bias. In terms of better stability of throughput across different speed accuracy biases, we recommend using throughput calculated with the effective width when comparing performance between multiple devices, multiple groups of participants, or multiple experimental conditions. For the evaluation of steering performance, we recommend the sine wave shaped steering task due to the stability of throughput across different speed accuracy biases.